let's review here at the board a little bit about SN2, or E2, sorry. Well, we will get into some SN2 comparisons down here in a second. And that's what I really want to get to, because there are some gray areas here. And we've talked about a couple of these nucleophiles being good SN2 nucleophiles, right? But here we are showing them as E2 bases. And they are basic. They're on the, the high side of the pKa. That's up around 15 or higher for TB toxide. So E2, what are we talking about? Well, all halides can undergo eliminations. And that's a key way to form alkenes. This is a preparatively very useful transformation to go from an alkyl halide to an alkene. And alkene's a very important functional group, and we'll see later a lot of reactions with alkenes. The halides, the weaker that halide bond is, the faster it goes. So that parallels SN2 reactivity like we saw before. The arrangement conformationally between the beta hydrogen that we're removing and the leaving group, the X group, if it's in the anti-staggered conformation, that's going to be faster. And if it's in a cyclic structure, we'll see if it's locked in that anti-diaxial arrangement. That's going to be the best arrangement for the elimination. And kinetically, those are going to be fast, okay? So we're implying things about kinetics here with these greater than signs, right? And same thing here with the conformation. Now, TB toxide, with all of them, primary, secondary, tertiary, undergoes elimination. Why? Because it's what? Bulky, okay? It's a weak nucleophile because of its steric size. But there is one substrate that TB toxide will do an SN2 reaction with. I mentioned that last time. Anybody think of that yet? What substrate will it do an SN2 with? There's only one. What is it? Methyl, right? If it's just MEX here, it still will do SN2. You may want to think about that. That's unhindered now. And there's no beta hydrogens to remove. So you can kind of remind yourself of the mechanism. That is a way to do a substitution with TB toxide, even though it's bulky. That's with the smallest halide, right? So yeah, examine the structure, and then it shouldn't be too bad. F oxide, is smaller than TB toxide, but with secondary and tertiary halides, it will do the E2 elimination. What about with primary alkyl halides? What reaction will it do instead? Right, SN2, okay? And we saw that before, okay? In fact, F oxide with secondary will still do a lot of SN2. In fact, it'll give kind of a mix. Kind of have to look at that. That's a gray area there, okay? But if it's tertiary, always elimination with F oxide. Primary, always SN2, okay? So there you see the sterics kind of playing a role, the sterics of both the leaving group and the nucleophile, right? And then hydroxide, that's a great SN2 nucleophile with secondary and primary, okay? So yeah, SN2 with secondary and primary. But tertiary hydroxide, it's too hard to hit the back of the orbital there. It's too hindered. And even little small hydroxide, because of its basicity, it's 15, right, on the pK scale. So that one will do elimination. So I think this gives you the whole story about E2, all the characteristics there. Any questions on those? Yes, please. Yeah, the question, will hydroxide do any E2 with primary, secondary? There'd have to be some other conformational issues or something hindering the approach there. Yeah, but generally for this class, let's just say primary and secondary with hydroxide will do SN2. I'm trying to keep things clear. I don't want to muddle too much in the gray areas here. Almost all the examples on a quiz or test will be very clear one way or the other, okay? And then we got this other eliminating base here, DBU. We talked about its structure last time. I like to use it again to talk about the mechanism, how we flow the electrons. And here's our alpha position where our leaving group is, right? And here's our beta carbon where the proton is that we're going to take off. You have to have two carbons to do an E2, okay? Because we're forming an alkene after all. And that's, why TB toxide with the methyl leaving group can do the SN2, right? There's no beta proton. So what do? I said this lone pair is the one that's actually the nucleophile, even though that's the more hybridized, the sp2 hybridized one. Those electrons are held a little more closely. You'd think that that would be the weaker base. These are sp3, but it's this resonance effect that we can look at that we showed last time. But there's the mechanism. So you think of this proton coming off, you know, it's not shown as H+, but this is indeed a base because it's grabbing a proton. Proton acceptor is a base. So we're talking about the basicity of these reagents. Here's where our alkene's going to form, and there's the leaving group coming off just as before. So it's really the motion of how many electrons? 6 electrons involved there, right? And then we get to DBU, which will have this guy protonated now. Won't draw the rest of the thing out there. But you see that that is resonance stabilized now. Whereas if you protonated the sp3 lone pair, you couldn't get that resonance. In fact, you can look at the pKa of this acid here. Now, the pKa of protonated ammonia, right, ammonium cation or a protonated amine, what was that pKa? Remember, that was one you had to know. What is the pKa of this? Well, before it was 9, right? But because of this resonance stabilization here, this pKa is 12, okay? So that's even weaker acid, which means what? This is an even stronger base due to that resonance. And that's in that range, the high range, right? Which makes this a good enough base to do this type of elimination. It's not as strong as TB-toxide. Tert-butyl alcohol is what, around 18? So that's even higher, even stronger base. But this one's strong enough. DBU is also important because it's a non-polar thing. This greasy part of the molecule on both sides makes it more organic soluble. It's more compatible with some leaving groups like that. Any question on the mechanism there? Anything? Keeping the basics straight there. All right. Now let's look at some other substrates where we've got some choices to make here. How about this iodide? Let's react that with sodium hydroxide. And again, sodium hydroxide, this is tertiary, so that's the next thing to look at, right? Charged reagent, hydroxide, O-, and tertiary. But what product are we going to form here? Let's see. We've got, at the beta position here, we've got a hydrogen. Is there another spot where we have beta hydrogens on this substrate? Yeah, where are they? On the ring, right? We got one here. Well, actually a couple. There's methylenes here. Is there another spot where there are beta hydrogens? Yeah, you'd say up at the top here, right? So which one's going to come off with one equivalent of hydroxide? Is it going to come off the methyl group or off the methylene? And what factors can we look at? Let's look at the methyl group first. Is that the product of E2 elimination off the methyl group? How many people say that that looks like the correct product up there? Anybody brave enough? No? Okay, one person. Yeah, that would be the product eliminating up here, right? Flow the electron. What about if we take it off there? Well, we're going to get, what, this product, okay? Which one is going to be favored and why? If you remember, we talked about last time the relative stabilities of different alkenes. And what did we talk about there? Yeah, anybody have an idea? Yeah. How many substituents on? 3 substituents on this one? Yeah, so a person points out that this one on the right would be more favored because it's more substituted. It's more stable, okay? So having 3 carbons on this alkene, and there were a couple factors there we talked about that have to do with alkene stability. Anybody remember those ideas? What do we say? Inductive releasing by the sp3 carbons and also hyperconjugation into the what? Pi star bond by the sigma bonds next door. So a couple factors that make this about 3 to 8 kcals per mole more stable than actually a di-substituted alkene. Okay? So the base will actually pull this one off in preference, okay? And that one will form at a faster rate there. And actually, this is a weaker bond. This is a more substituted carbon. So you can look at the bond association energies also and see that that's about 93 or so kcals per mole. This one up here is around 100 kcals per mole. So this is actually the weaker bond, and it gives you the more stable product, okay? And those factors are borne out in the transition state leading to this one. By Hammond's postulate, we say that those factors affect the kinetics leading to this more stable thermodynamic product. So this is a thermodynamic argument. This is the more stable one, but actually the pathway leading to it is faster also, okay? So there's a couple factors that lead to that. TP toxide, same thing. Okay, even though that's more hindered, sometimes students get hung up on this. Well, TP toxide's so bulky and hindered. I emphasize that a lot. Why doesn't it go for the primary position, not the secondary? Well, it's just grabbing a proton. So sterically, that's not a problem. Remember, the steric factor is the backside attack here to do SN2, which is now highly disfavored, even with hydroxide. So this is our product. And on a Quizzer test, if you just put that product, the major one, you get full credit. Don't try to overanalyze things and show a bunch of products, especially if you don't say which one's major. The TAs will take off points, okay? Just show the major one, and you're off the hook. There is some of this formed. I think it's like 10 to 1, but we're not going to worry about that. We're not going to make you keep track of all those little ratios. Just go for the major guy. Is that okay? TAs, yeah, they're nodding their heads, thumbs up. Just show the major one, and you'll get full credit there. Okay, how about this one? Couple of benzene rings on here. There's bromide, okay? And let's use ethoxide this time. So yeah, secondary with ethoxide, we're going to get mainly E2. And where's our beta hydrogen? It's right there. And so it's really the only position, right? This one's not the beta hydrogen. That's the alpha hydrogen. We don't pull that one. To do the mechanism, the base pulls that flow in, and there's where we put the alkene. And the product is this. It will be the trans product. Will it have a little bit of cis product too? Yeah, but that's minor. Remember where we said alkene stability? The trans alkenes are more stable, having the groups across from each other, okay? So that's the only one you need to put in there. How about this one? Let me get another board up here. How about this one? I think we have a few more choices on this one. Oh, yeah. Another tertiary bromide. Oh, and with another methyl group here. Okay. And let's do TP toxide. And where are we going to eliminate here? We got to analyze at the beta positions and see what hydrogens might be pulled here, because we're doing E2 elimination, right? It's not a methyl bromide. Okay. Tertiary bromide. And let's see, do we have beta hydrogens up here on this methyl? Yeah, okay. That's a possibility. Do we have beta hydrogens over here on this methylene? Yeah, okay. 2 actually. So do we pull that one? Are there any more here? Is there another possibility for, yeah, somebody's nodding their head. I think this one right here, right? So we actually have 3 choices here, a methine, a methylene, and a methyl position. Which one is going to be favored? Maybe we'll draw them all up here, and then we'll decide which is which. Let's see, if we pull this proton here, we can kind of do the mechanism to help ourselves out here. What will be that product? Let's see, we'll have alkene exo to the ring. Is that the product that would result from deprotonation up there? Okay, how about this one over here? Same flow of electrons. Where would the alkene be? Be up there now. And we'd still have, what, this methyl and that. Okay. Is there another one here? Oh, yeah, the methine. Forgot about this one. Okay. What about that flow of electrons? And what product would that be? Let's see. We'd still have the cyclohexane in this case. And I think the 2 methyls would be there. Verify that those are all the the correct E2 elimination products from there. Now the tough thing, maybe, which is the major product? And if you drew all three here on the test and just left it like this, we'd have to take off some points, okay? If you drew all three and correctly identified the major one, that would be okay. And if you just drew the major one, that would be better, easier for us grading-wise. So which one do you say? This alkene, how many carbons on this? 1, 2, so that's di-substituted. How many carbons on this alkene? 1, 2, 3, tri-substituted. Oh, and this one, right? How many? 1, 3, 4. Okay, so tetra substituted. Which one would be more favored thermodynamically? Yeah, the tetra substituted one by quite a few kcals per mole. So actually the weaker bond is at this methine position. And even though TB toxide is hindered, it'll still be able to grab that, okay? And a hydrogen pointing out, is getting it out of the structure. It's not this backside attack idea. It's deprotonation right here, which is fine, even with a hindered base like TB toxide. And this is indeed the major. So as long as you just showed that or said major on that, you get full credit. Okay, that's a little bit of a tougher problem, I think. Questions on that? All right, we have to do a little bit on E1. And I kind of regret to do this. E1 is not an important reaction because it's not preparatively useful. It's often just a nuisance. It's often just a minor product for SN1 type reactions. So what do we mean by E1? Elimination, unimolecular. It's a stepwise process that goes through the carbocation, just like SN1, right? Where we ionize first with a neutral nucleophile. Okay, not a charged one. Or, a non-nucleophile. Okay? And if it's just in a non-nucleophilic solvent, the halide will just eventually fall apart and eliminate. It'll be very slow. In general, all of these are very slow because they all go through carbocations, okay? There's no charge nucleophile here to do the bimolecular E2 or the SN2, okay? So it's often mixed with SN1. You can already see the factors there. And what type of halide? Tertiary, faster than secondary. Much, much faster than primary. In fact, with primary, with a neutral nucleophile, usually we say no reaction. If you show the E1 with a primary and a neutral or non-nucleophilic thing, yeah, that's fine, but recognize it could take months or years for that reaction to go, so it's just not practical, okay? Feel free to say no reaction. In fact, there's one on this quiz, I think. You might be able to see where it is. So what are we talking about here? Here's a tertiary that will be faster, and here's a nucleophilic neutral solvent, and there's our product. And yeah, the thing does get acidic. It will form hydronium ion. In fact, you can watch the pH drop and become more acidic. That's a way to track these reactions. But even this one's slow, okay? Why? Because it involves ionization first, goes to the carbocation, and that's a tertiary carbocation. That's why it goes at all, I think, in this case. And then water attacks. It's the solvent. You could call this a solvolysis reaction. And that's what we got to before, right? And that's the major product. Well, we had to lose the proton. Sorry, I'm not showing the last step there. So this is stepwise thing. But what else can occur here? Instead of the substitution that I'm showing there, that's the SN1 product, right? How do we get to the alkene? Well, we have water taking that proton off. You see that will get you to the alkene, okay? And, if you have a highly substituted alkene, that can favor E1 elimination, or like I said, a non-nucleophilic solvent, even something like acetone, which is very non-basic, or even something like toluene, okay? If you heat it up, sometimes you'll get more of the elimination product. And that's kind of an entropic effect. You're breaking the molecule apart and eliminating something off, and at higher temperatures it will favor that. In fact, let me give you some data here. I've got the numbers on a couple of these reactions. So how about this one? Water at 80 degrees and water at room temperature. So yeah, I've got the actual yields here. Here's the E1 product, and that can be obtained at 83%. Okay, higher temperature will favor the elimination. What's water at room temperature? Don't worry, this is from chapter 7. Everything we told you in chapter 7 is not a lie now. We're just giving you the rest of the story. This is what your SN1 product, and what's the yield here? 80% yield if it's done at room temperature. Okay, so there's kind of a gray area right on the edge where you kind of have to choose there. But if you specify the conditions, you can get one or the other. But you know, this is super slow. Both of these are super slow. If you want to do an elimination, don't wait around forever. The best thing to do here is TB toxide. Then it's done in minutes. You get a very high yield. If you want the substitution, fine. Use water, but do it at room temperature. Okay. You see, this is not practical to let it just sit around in water. It would take too long. Okay. So we don't use E1 by choice. It's often just a byproduct of reaction, so don't worry about it. Okay, questions on that? Enough on E1, okay? Don't make it a big concern or focus there. Let's get into the main event now, which is going to be the stereochemistry of this elimination. What did we talk about? The hydrogen and the leaving group in a typical E2 reaction. We want the hydrogen and the leaving group anti. And that's a conformational thing. Remember the dihedral angle, omega, we said by the Newman projection, what's that angle? If they're anti, they need to be what? What's the number of that dihedral angle? 180, right? So that's what we're looking for there. And we can draw that out and verify that. That's a consequence of the molecular orbitals, the mechanism of the reaction. So we'll emphasize that a little bit and show you some examples of that. Here's the first one I'd like to talk about. Let's have a diphenylethylene with a hydrogen and now a methyl in the back and a stereocenter here with a bromide in the back. Let's see, what is that? There's a couple stereocenters there. Let's keep track of them. This is what, S? And this is R. And if you do this reaction with sodium ethoxide, you get only this product where the two benzenes are trans to each other. So there's some stereo electronic argument we have to make invoking this dihedral angle here. So here's our beta hydrogen right here, right? You can kind of see it when we use the base to take that off. We're going to flow the electrons in there. You can see, oh, those two phenols, yeah, they look like they're trans to each other. The Newman projection's a little better to see this, though. Okay, so let's put our eyeball where? Right here, and look right down that bond. Okay, that's your eye. Or make models. Okay, and verify the thing. And what is it going to look like? It's going to look like this. The hydrogen in the front is going to be up. Methyl's over here. Phenol's over there. That's this carbon. And then there's also the carbon in the back, right? And we want to have the bromide down because we want the bromide, the hydrogen, 180 staggered to each other. And the phenyl here is on the side. And that's where we want it. We want the two phenols trans to each other. You can already see the stereochemical relationship between the two. And the hydrogen here is right there. And we can do the mechanism from this Newman projection too and see the stereoelectronics borne out here. Grab that proton, flow the electrons down in the back. That's where the sigma star is, right? On the back of this sigma bond. And as those electrons flow in, we flow the leaving group off, and you can see, yeah. And if we flatten this guy down, yeah, phenyl there, Methyl there, hydrogen. Oh, it's already up there. Redrawing it. Okay. Directly goes to this. Okay. See the phenyls trans to each other. The hydrogen and the methyl are trans to each other also. That's the only product. Here's another one you can do. How about if we take the diastereomer of that? Let's take the S and the S. So I think we already had S here. And now we have, what, S here? Yeah, we inverted that stereocenter. These are diastereomers of each other. So chapter 5 is relevant. We're combining stereochemistry now with the mechanism, now with the E2 products, right? You'd have to draw another Newman thing here. So you'd have this one in the front the same way. But then when you put this bromide down here, look, then this phenyl would be over here, and the hydrogen would be there. And this one gives this product. Only, okay? These are exclusive products. We say it's a stereospecific reaction that's governed by what? The mechanism of that anti-relationship between the beta hydrogen proton being removed and the leaving group at the alpha position. Stereospecific reaction. This is the only product here. This is the only product here. Okay? A consequence of that geometry constraint now. I consider this to be a very hard problem. Okay, I'm not putting a bunch of these on test 2, but there might be one or two like this that'll be more of a challenge where you got to combine, synthesize different ideas, principles we've talked about. So this combines the idea of what? Stereochemistry from chapter 5 with the detailed mechanism in chapter 8 here. Questions on this though? The Newman projection can really help you out there. This one, make a model and clearly look at the relationship between those two, and then you'll see, why it results in that way. Okay, questions on that one? That's a harder one. Let me do a cyclic one now. Let's get cyclohexane going. I got my model here. This is again a harder one. So let's see. How about trans bromo tertbutyl cyclohexane versus cis? These are cis-trans isomers of each other. They're both achiral because of the mirror plane. You don't have to worry about stereocenter. But the relative stereochemistry, the cis-trans stereochemistry, and this will say something about the kinetics. One of these is 500 times faster than the other. Okay, so the relative rates here of the reaction, 500 to 1. Which one reacts 500 times faster here with sodium ethoxide? You can't tell, right? They're both secondary halides. How are you going to tell this one? What do we have to do? Anybody have an idea how we're going to approach this problem to solve it? Yes. Draw the chair. Yeah, I've got the model here for a reason here. So draw the chair, and what will we be looking for in the chair to get an idea about the kinetics of this? Yeah. Which one's equatorial, which one's axial? What will be the optimal E2 pathway for the elimination? Yeah. Halide in the axial position, and one of the beta hydrogens has to also be axial. That will give us that anti-relationship. So let's start out here by drawing them. Let's do this one here. What would it look like? How about like that? And tertbutyl has an A value of over 5 kcals per mole. So that essentially locks the cyclohexane in this conformation. We got the tertbutyl, equatorial, okay? So we've got that arrangement. And then our bromide is trans to it, so it will be what? Also equatorial, okay? That's the conformation of this one. That would be the major conformation. Let's do this one over here. We'd have this arrangement. Again, the terp-butyl equatorial, it's down. Draw the hydrogens in too to keep track of it. And remember, any group coming off equatorial is parallel to these opposite lines here in the ring, right? And the axial ones are always parallel to the axis right down the top of cyclohexane. So keep track of it. Make sure you draw those clearly and distinctly. And then we've got bromide here, which is now axial, the magic position. Anyone want to make a prediction? Which one's 500 times faster, the one on the left or the one on the right? Yeah, the one on the right. And he said that very boldly and very quickly. Why? Yeah, he's saying when it's axial, it's much easier for the base to eliminate it. But what do you have to look for? You have to look at the beta positions here now. And see, we've got two beta hydrogens. And there's your magic axial-axial arrangement. And that's perfectly suited for the stereoelectronics of the mechanism. Because we're going to use the base now to grab a proton. It doesn't matter which one. They're both the same. It's a chiral molecule. And this will liberate those electrons to flow into the magic sigma star, which will be right on the back of that orbital. You see where it is now. It's also axial, sticking straight up, right? It's on the back of that leaving group bond. So there's your sigma star. The sigma bond here, the old sigma bond, will become the new lone pair on the leaving group. So I think that will, let the electrons flow in there. And our product, from that one, will be this, okay? And it'll happen faster because they're coaxial. But what about this one here? What if we grab that proton? Will that be the same product? Now be careful. I said the starting materials are both what? Achiral? They're not stereocentered. But is this a stereocenter now? A couple people were saying, yeah. And you can see it's a different location here. You're tied there, methylene, methylene, but then you get to what? Methine versus methylene. So this will have a higher priority group right there based on that one. So you can assign the stereochemistry there. This is indeed chiral now, okay? But wait a minute, we had an achiral starting material. So we can't create an anti-pure chirality out of nothing. We're going to also create what? The opposite enantiomer here, which would be right here. Now, where did that one come from? That came from the other axial hydrogen, you can see. So a mixture of two enantiomers, and these are indeed enantiomers of each other. This will be optically inactive, and it will be racemic, okay? So if you took the optic rotation of this product, it would be 50-50, and that would equal out the plane polarity rotation to still be zero there. If you had a chiral base, you could actually prefer one proton over the other. But we're not getting into that. That's an advanced topic. But you can kind of see the principle of it, right? So here's the two spots. There were two equal beta hydrogens right there. Okay, this one goes. It's 500 times slower. It's equatorial here. Well, wait a minute. Let's examine these hydrogens. We have an axial one here. How come that one's not coming off fast? Well, where is the sigma star here? Here's the sigma. The sigma star is underneath, inside. And look, this sigma bond's not coaxial or coplanar, you can say with that one. Whereas this one, you can see these sigma bonds are right coplanar, the sigma star. Whereas here, it's tucked underneath, right? Because this is equatorial now. This does not mean these don't go. You can do this reaction from the half chair conformation, which is higher in energy. And these hydrogens on the side will get somewhat, coplanar with that. They're not perfectly 180, even in the half chair. So that's puckering this carbon up a little bit. You see, that's a higher energy conformation. It's not the clean chair conformation. So this one will be slow, okay? But it will give those same products, okay? 500 times slower, okay? This one's done in minutes or even seconds. When you start to monitor this reaction, you'll already start to see product. This one takes many hours. I think it's 12 hours for it to go, okay? So the kinetics can play an important role there. All right, questions on that one? Again, that's a tougher problem, right? It combines the idea of the chair conformation. Yes, please. Yeah, if you're asked to fully analyze it. Now, this would be a right-on type problem, and one like this has been on whole tests. It's a common type of problem. So bring your models to the testing center if you're unclear on this. We're still having trouble drawing some of these, but yeah, so it would be important to analyze fully the problem and show both. So the question is, would you have to analyze both or show both products? Or, fully analyze the faster one if that's all we're asking. So read the instructions for the problem. That'll give you an idea of what you need to put for your answer. So I'm sorry if I can't fully answer that question, but kind of depends on what the wording of the question will be, but hopefully it's clear. But I think for the purposes of classroom discussion, it's good to go over both of them and clearly see why one is much faster than the other. Is that clear so far? Yes, please. Right. So the question is, why can't we use the other flipped chair conformation of that? Yeah, that's what the person's asking here. Well, yeah, if we flip that, we'd have this conformation. And we'd have the bromide indeed now axial, and axial here and here. Well, what's wrong with this conformation? And by the way, it's very wrong. This would be a tiny amount at equilibrium, highly favoring this one. And it's because of what here? Somebody was raising their hand. Anybody have an idea? Yeah? Yeah, the equatorial for especially tert-butyl, the A value is like 5.7 kcal per mole, which makes it 99.99 to 0.0001% here. So this is a very rarely populated conformer. And so that would contribute to this being very slow. I think the half chair, keeping this pseudo-equatorial, is better for getting these in this anti-arrangement. Make a model of it and you'll kind of see. But yeah, if you analyze that and you'd say this is a very minor thing and that's why it's slow, you'd probably get full credit too, I think. Yeah. Okay. Good. Let's see if we can do a couple more here. Yeah, I want to get to reviewing overall these reactions too. So let's maybe just show one more of the chairs here. And how about this one where we've got them 1,3 to each other? And maybe isopropyl. Oh, and I don't have the relative rates here, but one is super fast, let me just say that. And one is much, much slower. It may not be 500 to 1 like before. Yeah, in fact, one will start to give some SN2 reaction also. Well, let's just compare the relative rates here for E2. One's super fast and one is very slow. So which one would you say? We'd start with the chair analysis again. And what would we have here? Well, we'd have the isopropyl up there and the bromide up there. Those are both equatorial and they're cis to each other, right? And here we have the equatorial isopropyl. And the A value of an isopropyl is about 3.8 kcals per mole. So it still highly favors the conformer with that equatorial. Although, the axial one could be there, but that would be less populated. And then where's bromide here? Well, it has to be down. In the back there, axial, right? These are trans to each other. So which one? You can already make a prediction. Which one is going to be faster, the one on the left or the right? The one on the right, okay? Because this is locked axial. You're going to get a couple different products here. I think you can see, which base did we say here? Oh, hydroxide. Okay, so sodium hydroxide. And that, like I said, gives a mix of SN2 and E2. But the E2 reaction is very fast because this one's there. The hydrogen there. Hydroxide is small enough to start to do some SN2 there, okay? In fact, that one will give a higher proportion of SN2. This one's locked in the optimal E2 elimination from that. And I think you can draw those two products. One has the alkene here, closer to the isopropyl. The other one is further away. These are both chiral to begin with, okay? So they're going to give different products, different properties there. But I think you can analyze that one in the same way, okay? Again, the key is always to draw out the chair and then analyze it and look for the coaxial, both the hydrogen and the leaving group both being locked in an axial position. And a big alkyl group on the ring will do that. Sometimes students ask, well, wait a minute, bromide's a big atom. Why are we putting that axial favorably? Anybody remember the A value for the halides? They're actually very small. They're just like half a kcal per mole. Why? That's a big atom. Well, it's a longer bond, okay? And actually, sterically, they're not nearly as big as an isopropyl or terbutyl, okay? You can look back at that chart and see the A values. It's okay to put those axial, as long as you have something else favored to be equatorial. That's usually a question someone asks. All right, let's look at alkynes here. Dehydrohalogenation can occur in a double-barreled manifold here. If we have dihalides, we can use two equivalents of strong base. And usually we use a stronger base. T-butoxide will do this, or amide, sodium amide. And we'll do the elimination here. The Zaitsev's rule applies. The more substituted one will go first. The methyl group, those are stronger bonds. The weaker bonds are at the more substituted spot. And that will give the more substituted alkene product. And our first product will look like that. Okay, that's indeed an E2 reaction. Okay, but we're using two equivalents here, or excess of the base. Why? Because we want to do another E2 elimination. Now we have a choice here, right? Hydrogen now is a different hybridization. This one's what? sp2? This one's sp3. We have a choice here. Okay. Which one's a stronger bond based on the bond association energy? sp2 actually stronger. You'd think, oh, this is the weaker bond, and base might take this one off, right? And that would give us what's called an alene. Alene means two double bonds on the same carbon, okay? And that one is not the product. So it's not just the bond association energy. We'd think that one would be the favored one to go. This is indeed a stronger bond here than this one. But look back in chapter 6, is that, with the bond association? So it's got to be another factor here, because the observed product is this. The alkyne, Y-Ne, okay? Alkene is E-Ne, triple bond alkyne is Y-Ne, and we'll have a later chapter where we'll get into that and do the naming of these, but this fits into the elimination chapter, so it's covered here. So why is the base pulling that one instead and putting the second pi bond there? There's two pi bonds and a sigma bond in alkyne. Review the structure of that. What other factors might we point to here? Look at the geometry of that hydrogen versus the leaving group. What is it? 180 degrees, right? And also we can think about what? The pKa's. We're removing a proton here, not a hydrogen radical, which is what bond association energies reflect. We're grabbing this and leaving these two electrons here with a negative charge on there, which is actually better if you're sp2 hybridized. The pKa of this is about 40. The pKa here of an alkyl sp3 hydrogen is about 50. So which one's more acidic? It's this one, okay? Even though it has a stronger bond by bond association energy, which is a homolytic thing reflecting the radical stability. Here we're using a base, so it's locked 180, and the pKa is a little bit lower. So that's why we favor here and give the alkyne and not the alene, okay? Now we can do the same thing if we have the two halides beta to each other. So this is what, 2,3-dihalobutane. Here we have what, 2,2-dibromobutane. We call this geminal. Geminal from Gemini, which means gemelos or twins in Spanish. Any Spanish speakers out there? Gemelos or twins? They're on the same carbon. These guys are vicinal or vecinos. Okay, they're 1,2 to each other. Okay, but here we got the hydrogens here, and we'll go to the same thing here with two equivalents. So let's use TB-toxide this time. We'll first go to this, and with the next equivalent, we'll take that one off. And look, we go to the same thing, the alkyne, okay? So it's a double E2 elimination, and there's a couple factors to look at there, mainly the 180 relationship and the pKa being more acidic. Not the bond strength. That's not the argument, okay? I think that's good. All right, let's start reviewing. We've got a couple minutes here. You okay with this? This is not a new reaction, really. It's a new product, we can say. But it's the same mechanism, same E2 guy, okay? Let's look at some reactions here. Let's review the whole thing. Well, yeah, I wanted to look at the overheads again, too. Maybe it's better to review right here. Okay, SN2, SN1, E2, E1. Boy, that's a lot of mechanisms, isn't it? We're giving you a heavy dose here, especially when all the variety of nucleophiles. The most diverse one by far is SN2, because we had, 10 or 12 different nucleophiles floating around. E2 is a little more focused, strong, bulky base. TB-toxides, where you hang your hat, all of them will do the elimination with TB-toxide, except methyl. Methyl will do a substitution. But how do you keep track of this? You always look at the nature of the R group, right? Primary, secondary, tertiary. What's the next thing you look at to try to figure this out? Yeah. Nucleophile. Charged nucleophile versus neutral nucleophile, okay? Charge wants to bring it on. When it collides, it has excess density. It wants to do what? Bimolecular one-step reaction. Collide and do what? SN2 or E2 if it's bulky, right? So that's the next thing you look at. And then you look at the size, the bulk of the nucleophile, okay? Charge. So we had F oxide, TB-toxide, which was a little bit of a deal there. But F oxide always with E2, okay? So how do we figure this out? Well, if we've got primary, secondary, that's mainly SN2 because it's less hindered, the backside attack. If we've got tertiary, well, that's going to be more SN1, okay? So those are the two things you can look at right away and kind of differentiate those, right away. So it's charged nucleophile, primary, secondary, okay? If it's a neutral nucleophile, tertiary, and secondary. The rates, though, change, the relative rates. The more substituents are faster here with SN1, being a neutral nucleophile, it's going to wait around for the ionization there. Okay, so those factors there. And like I said, the bulk of this is key there. Yeah, we'll start doing this next time, but let's just go through the rest of the overheads here briefly. I think we actually finished chapter 8 then, but we'll review on Friday and have the sample test also. So there's your typical what? There's your SN2 nucleophile? No, that's what reaction? That's an E2 elimination, right? Charge, strong base, and there's the elimination. The 180 relationship there. And it is just one step. It's bimolecular, E2, that's what it means. And then we had DBU, which can do the elimination right here. Here's a substrate leading to a prostaglandin. It's part of a synthesis of that drug. Well, there's a review of the mechanism that we did at the beginning of the chapter today. Here's another application with a primary leaving group, but with TB-toxide being so hindered, there's the elimination. Here you use excess because you've got an acid there. One equivalent just takes off the proton. Okay, but DBU can also do the elimination. Here's the E1. You can look at the carbocation being formed there. And then the non-nucleophilic neutral, nucleophile water in that case. And yeah, the 180 relationship is the one we've been talking about there. And yeah, we'll start to review there, and we'll get into this, and we'll review here. And I've got this decision chart. If you want to be looking ahead,